I was asked to take a look at water management relative to climate change, and some of the things that we might think about or need to take a look at as we look in the future and what your operations really might need to consider as we do have to adapt. As Aaron so succinctly showed us data today of weather changes, but that ultimately it is affecting what we consider as climate. So taking a look at those climate changes, I'm going to take a look at some of them specifically here in central Ohio. So I've got some data that we're going to take a look at from the Columbus area. But it's also, I want you to think about it in terms of how it's going to impact soil erosion. And I think that's a really critical one when we think about water management, whether that's water that we're storing at our facilities, in our fields, or that's water that's being lost during the erosion process, the runoff process. We also have to take into account water storage capacity in our soils, as well as cover crop and residue management. So this is this year's data from NOAA, and so if we take a look at Columbus, and we know that in this region here in Ohio, we have had heavy rainfalls, as we can see down here in the. Let's see if I can get that to work. I'll use the mouse. There we go. We can see down here. Is the mouse showing up?
No.
All right. I don't want to do that. All right. Let me get my technology. Do I have a pointer, Aaron? Yes. Good deal. Okay. So if we take a look, obviously we have a really high rainfall events this year, and you guys are dealing with that, and obviously experienced that last night. Might be part of the reason there's so many people in the crowd today, right? And but I do have some good news for you. We will have a drought. You know, and that's just the nature of the game, right? Is that we are going to have a drought. But I think one of the things that to take away from Aaron's presentation is that in Ohio, we're very likely looking at some swings in not only temperature, but precipitation that maybe many of us haven't dealt with in our lifetimes, and historically, at least in our history through Ohio, maybe has not been something that we've had to deal with on a regular basis. You know, a reminder, Tropical Storm Barry is a good reminder that when we take a look at these events like a tropical storm, really we're just looking at that energy transfer from those equatorial regions. Obviously, we call them frequently those tropical regions towards the Arctic regions, and we're looking at that balance of that shift. And it just so happens that in Ohio, we tend to be right in that flight path, as Aaron mentioned, because we're buffered on the west by the Rockies, and so that natural tend is for those, and we see it all the time as those flows come up, and we have that movement through the profile, through the air profile. And so that brings us, you know, to take a look at, well, what is happening in Ohio? And so I'm using some of the data, and I know Aaron's got a lot, you know, he has some quite a bit of data that he showed us earlier, but I really wanted to focus in kind of here on Central Ohio and just take a look at some of the things that we have seen. And so when we look at Ohio, this is the gray is the temperature, the maximum temperature that's averaged over the year, and you can see those variations that Aaron talked about, those annual variations. But certainly, just like the dog walker, right, the trend in this case is not up as much as the one in below, where we see those average max or minimum temperatures increasing. Or if we look back at, and this data set is from 1948, so this was from Port Columbus starting in 1948 to 2018, so the last roughly 70 years. And so we see that our maximum temperature on an annual basis only increased about 2%. But if we look at those minimum temperatures, those daily minimum temperatures on average throughout the year, we've seen about a 9% increase in temperature. All right. So just thinking back to that tropical storm, right? That's 9% more energy, if you will, in our environment around us.
How much of that temperature increase can be attributed to the fact that Port Columbus was out in the country in '48 and is now in a highly developed
That's
concrete, asphalt
that
environment?
would be a question I would have to pass on to Aaron, because I don't know how they maybe have accounted for that in the data set. All right. So, but that's certainly something to factor in.
We all know it's hotter in Columbus, maybe it's politicians, than it is out here in the boonies.
Not going to comment on that one. All right. Here is actually the number of days with temperatures greater than 90 degrees. Now, you may have heard from my bio that I've lived in some relatively hot places. And so one of my first summers in Ohio, when I heard them talking about, they were actually counting up the number of days that it was above 90. And I thought, man, this must be like close to heaven if they're counting the days in the 90s, right? But if you look at this, actually, those number of days is actually fairly flat. But I think if you, as Aaron talked about, there was a shift. Here we have a period here where they were fairly low, and they've been quite a few of them in the last few years. Now, frost-free days, and I didn't break it out the way Aaron did, but just taking a look at frost-free days, if we take a look at 241 on average, if we look at this end of our graph, up to on average about 265. So that's about a 10% increase in frost-free days. And we, as Aaron talked about though, just frost-free days may not mean more days in the field that are workable, right? Which is one of the things that many folks have experienced this year. Now, total rainfall, as Aaron pointed out, has been increasing. If we look at Port Columbus, we're roughly about 36 inches in 48, and now about 42. So that's about a 20% increase in precipitation. And you can see that we've had some very dry years during that period, but also as last year set a record. So those increases, we see this trend for increase in precipitation, as well as the number of days that are above, that receive a 1 1/4 inch rainfall. Now this is the one that really jumps out. When you look at the number of days where we have rainfall events greater than 1 inch and a quarter, all right, that's about a 91% increase. If we look back at the early in the 1940s, beginning that period, roughly we might expect about 3 per year. Now we're up to almost 6 per year. And now those size rainfall, I'm sorry, not rainfall events, but total rainfall, folks, that is a huge amount of energy that's entering our system compared to what it was in the years past. Because when we think about those raindrops as well as the atmospheric temperature are both just different forms of energy, aren't they? Right? That raindrop has energy. In fact, we know water has a very high capacity to store energy. And so when we see that amount of water coming into our environment, we're increasing dramatically the amount of energy, the amount that we're experiencing in our environment. Now that's going to make some changes and shifts in our management decisions. And in particular, we're going to see tremendous shifts when we think about soil erosion. All right? Because really, when we think about erosion, it's that energy is the driving force for erosion. Depends on what part of the country you're in. Here, water erosion is our driving force when we think about that. Other places, they're going to deal with water and wind erosion. And I know, having lived in some areas where you have to take into account dry climates, then wind erosion can be a more important part, or certainly an equal part. And if we look at many places in our semi-arid regions, the amount of wind erosion and water erosion are equal when you get out into Kansas and Oklahoma area. So when we take a look at that energy, it's not just the total rainfall. So we saw the total rainfall was increasing, but it is also the intensity of that rainfall. Now that data I showed you isn't broken out, and I know, Aaron, I want to sit down with Aaron and talk about that a little more in the future, about what we're seeing relative to the intensity of the rainfall, because that intensity of the rainfall has a tremendous impact on the amount of erosion that we will experience, that you're going to deal with in your fields, all right? And this is the for those of you who aren't familiar with it, maybe you've heard of the USLE, Universal Soil Loss Equation. This is the revised version is what we use today. And I know there's a number of models out there that are addressing things like soil erosion, but as of today, NRCS still uses Russell or Russell 2 today for our estimates of soil loss on an annual basis. And until they switch, I'm gonna stick with using Russell. And in part, it also because it's a little more straightforward to understand than some of the other models that are out there. I highlighted two components of the Russell equation, the R factor and the C factor, all right? The C factor we're going to get to in a minute. That's the one that you have most control over. Really, the R factor is what we're talking about today relative to climate, you see? Because that R factor takes into account what we might consider the energy in that environment. So I've got to, and I apologize that we don't have a nice digital figure of this. I've tried to find a nice digital map of these isoerodents, all right? And I can't find one. This was, now, as you've seen from both some of the information I've shown, but certainly what Aaron has shown earlier, is that a map drawn in 1968 may not match what we have today. And so that's certainly one of the complaints about Russell, is that we need to update our R factor, which is what this map is. It's a map of the R factors across the US. And it's not a perfect analogy, but one way to think about the R factor when we look at that Russell equation, it's a measure of the amount of energy that is in the environment that your field experiences, all right? It's not quite perfect, but it's close, all right? And that R factor takes into account two things: the total amount of rainfall and the intensity of a 30-minute storm. Those two factors go together, and they sum that up throughout the year to give us this value, this R factor. And so if you look at that map, all right, and we think about Tropical Storm Barry that we saw on that previous graph, right? New Orleans is just like right there in the sweet spot on a catcher's glove, isn't it? Right? If I'm a storm and I want to hit the bullseye, I'm going to hit New Orleans, correct? And so it just funnels the geography, and the landmass funnels those storms right up that direction. And so if you look at this isoerodents, down here and in the back, it may be difficult to see, but if we look down here at New Orleans near that bullseye, it has an R factor of 700, all right? And now you can see how that energy then, if another way to look at it, that energy begins to disperse as it goes across the continent. Now, and so these lines are set up this way to take into account how each region, and if you've ever run the Russell equation, that's what goes into that county information. In the climate data, they pull in what that R factor is for each county, all right? Now, it goes from basically 700 to about 30 by the time you get up to the Canadian border, and 30 if you go up to Maine. Now, one of the things that we see is out here in this area through Kansas, a little bit in Nebraska, Oklahoma, and West Texas, as you see those lines get very, very compressed, right? They get very close together. And so that energy changes very rapidly as we move towards the Rocky Mountains, and it drops. So you see significant changes. So if you're down here in this part near the Louisiana border, you're about 400. And by the time you get up to Kansas, north part of Kansas and Nebraska, you're down to about 30, which means there's a lot of that energy has been dispersed across the landscape. Well, what does that mean for rainfall events? All right. Well, what that means, if we take a look at the rain intensity or the storm intensity, it really dictates how you manage your erosion. Because when we look at that the R factor is the dominant factor in that Russell equation, right? With numbers of 100. And if we look at Ohio, we're very fortunate. And this is one of the reasons when I came to Ohio, and started driving around the state, around different county roads and state highways, and I would see some of the hill slopes where I was watching people, cultivate up and down the slopes. And growing up where I did and working in the areas where I could not imagine anybody would plant their rows with the slope like that, because your field would be gone in those areas. And so that's one of the things that we've been blessed with in Ohio, is that our erosive energy historically has been fairly low. If you notice, we essentially have two isoerodents across Ohio. We've got 100 and 150. So our energy, for the most part, historically has been fairly low. Now, one of the things that we need to think about, though, is, will that remain that way? Will it, or are we seeing some changes? This is a paper that just came out a couple of years ago. Some folks down in Tennessee. And so they were taking a look at the erosivity, so that R factor. And so they were looking at some areas over here in kind of east central Tennessee. And what they found is that with the data they have, and then projecting out with the models from today, so using the data up to 1999 that was calculated, they had a value of 240 for their R factor. Now, when they project that out to the end of the century, the R factor is up to 297, which is about a 24% increase. A 24% increase in the amount of energy that's in that system. What that means is that they've got 25 times more energy ready to move the soil, transport that soil off of their fields in Tennessee. Now, if you have 24% more energy, what does that mean for the management practices that you're using in your soil conservation practices? And so I think that's one of the things that we have to take a look at in Ohio and consider is, as we begin to see some shifts with these storms, if we have increasing number of storms coming in to that Gulf area, it will eventually, in the summation of it, we will see more erosive energy in our environment. And so some of these maps that were developed 40 years ago, 50 years ago, we're going to have to go back and probably revisit those, or as some of the new models are taking some of this into account. So basically, we do have more energy coming into the environment, all right? So how are we going to handle that? What's the value of a raindrop in your operation? Have you guys ever sat down to consider that?
It depends upon the year.
It depends on the year, exactly. And that's going to be our challenge. Having worked in some areas where we have these incredible swings, if you will, this incredible variability. I know Dr. Brzezinski can attest to this, but I remember my first year I moved to Oklahoma. The first year I was there, it was heat of 113, all right? High temperature, 113. And then the next winter, so the next February, minus 18, right? And I thought, where in the world did I move to? It was roughly 130 temperature degrees swing in less than a year. And I think that. Now, I'm not saying that we're going to experience that, but I think those are some things we've not necessarily had to deal with. And I think that's part of what Aaron was showing with his data, is that we're starting to see maybe some of these swings that we have maybe historically haven't seen. And so those are some things, some questions we ask about is, how are we going to handle this? We will adapt. We have to adapt. Agriculture has adapted for centuries, right? And we've seen changes throughout the years, but we will have to adapt, and it's going to take some different strategies. One of the things that maybe we've not had to think about in the past is, what is the value of a raindrop? But that's going to be a challenge, because if we're in a climate, if we're in a zone where I've got 1 year I'm in drought conditions, and the next year I'm being flooded out, which one of those do I manage for? And it's a tough one, right? I know as you get closer to say that Kansas-Missouri border, for example, and I know that's right on that zone. If you look at it, do I irrigate? Do I spend the money to irrigate or not? Because the frequency of having a drought year during your cropping season is fairly high, but is it high enough to, how frequent is it enough to pay for that irrigation system? Those are going to be some questions that people may have to begin asking. But what is the value of that water drop? How do I turn that, right? I'm trying to turn that into photosynthate so I can turn it into some sellable crop, some marketable crop. And so how valuable is that? And do I need to, am I trying to remove it in a year like this? Or are we going to have some swing years where now I've got that drought year and I'm trying to store as much as I can? You know, this is one of the things I think that helps is a good reminder, and this is a picture one of my former students took. He had a great microscope set up. And really, I use it because I think it really illustrates when we think about that pore space and what we're trying to manage when we think about our soil resources. And when we look at these pores in this soil, remember all that water that you need those big pores like that to get that water moving through as fast as possible. We call it drainage, right? We want a well-drained soil. But your crop depends on this film of water that's right next to these soil particles and all these aggregates. Unless you're growing rice, and by the way, if unfortunately we do have the climate of Little Rock by the time my career's or towards the end of my career, or maybe when I retire, if anybody wants to grow rice, come talk to me. I've got a little experience with rice production, and so we might be able to work out a consulting gig here after I retire. I'll have to be honest, the first time I heard Aaron share that analogy, I was not excited about that because I've already been down in that and farmed in that region. And growing rice and cotton, I just wanted to learn how to iron cotton. I didn't know how to grow it. Rice, we can work with that. But when we take a look at our crops, when we think about our production systems, whether it's corn, soybean, forages, wheat, etc., we're really managing this film of water around the edge of those particles, right? That's what we're after. And so that soil management, that soil erosion, and I didn't mention this, but if you think back to that shift, all right? So let's say you're in a zone that was in Ohio has an R factor of 100. If you now are in that 150 range, you just increased the erosion, the potential for your soil to erode by 1.5 times, right? Have you changed your management practices to reduce your soil erosion losses? Otherwise, what we're doing is we're losing that storage capacity. And so they're linked together when we think about the water storage capacity and the erosion capacity. This is from the NRCS web soil survey information. And this is just general. This doesn't take into account any soil loss that you may have had on your particular fields. And so if we look on average, some of the more common soils, we think about the Paulding, that's available water storage, 3.3 inches in that profile. Claremont, we're down to 11.5. But remember, that's water storage, but that doesn't mean that, I'm sorry, go ahead.
How many feet of soil?
It's going to depend, that's on the profile. So that's for a soil profile, not necessarily per foot, okay? So if we take a look at these though, all right, this is assuming that there's not serious erosion that has taken place, all right? The other part of this that doesn't take into account is plant stress. When does your plant start showing stress? Roughly when about half of the plant available water has been used. Now we're going to start looking at some stress deficits, right? So when you look at some of these soil profiles, there is not a lot of storage capacity to begin with. And so then if we're losing any of that profile, now we've decreased that capacity to store water even more. So when we think about our soils and how we manage that, it's going to be really critical moving forward of looking at that water deficit, understanding how to manage it, looking at some of the technologies that are going to be that are out there today. When I look at some of my site-specific information about what my crop usage is, what my respiration rates are, what my water balance going into the season is, and how that's being used effectively, and those may be some decisions that we've not had to deal with in the past But if we continue to see warming temperatures, warming night temperatures, which means that that respiration doesn't shut down near as much, because respiration is certainly temperature driven. And so we may see increases in water consumption because of those higher evening temperatures when the plant doesn't shut down in the evening. So all of those things can compound to put stress in a system that you may not have had to deal with in the past.
Jeff?
Yes?
Question on that last slide you had there.
Yeah.
Those numbers that you've got there under the inches,
Yes.
storage capacity, it seems to me that's going to vary a lot by farm. Somebody with a Kokomo, if you will, that has pounded that soil for the last 25 years, are they still going to get that 9 out of there?
Good question. Hang on a second. I'm going to come back to that in just a second if you don't mind. All right, we're going to get there. So, if we take a look at the management, all right. So we've kind of shifted away from that energy. Now let's take a look at those soils in that system that you're working with. Your soils on your particular farm, all right. We're having to deal with loss of water stable aggregates. You know, that's one of the things that we experience over years and years, after years and years of cultivation, is loss of water stable aggregates. In other words, the proteins that kind of help bind those soil particles together and create those nice aggregates, so we get that nice pore that we saw in that picture. Those have been broken down because we've stimulated the bacteria and the fungi to decrease those glues, if you will, that are holding those particles together. And so what we have to take into account is how much of that water is moving into the soil, all right? Not only how much is striking the surface, how much is moving into the soil, and that's where we get into something called soil sealing. We also have to take into account the amount of effective precipitation, all right? So in Columbus, if somebody was to ask you what the average precipitation before Aaron's talk, what would you say in Columbus? Upper 30s, right? Almost about 40, all right? What's the average precipitation in Tulsa? Nobody in here knows. Average precipitation, actually it's 44 inches per year, right? Now, how many big corn operations do you know in Tulsa, Oklahoma? There's not a lot, that's right. Now they can grow corn there, but they roll the dice even more, so maybe you lose your crop 3 out of 5 years or 2 out of 5 years, right? Because of drought conditions. And so there's also this thing about effective precipitation. How much of the precipitation you have at your location is actually being used effectively to be converted into biosynthate or photosynthate and into biological projects or products that you can sell. And so there's both the amount of precipitation, but then it's also driven by evapotranspiration. And there's a lot of that aspect too that's going to have to be analyzed and evaluated in the future about how that's affecting your current production practices. All right. So if we take a look at those water stable aggregates, all right, how much of that water is actually moving into and being stored? That was your question? Yeah, and so it's really a huge amount of that's going to be driven by these water stable aggregates. How much soil sealing is taking place? All right. Number of years ago, I worked with a guy out, and actually, I understand that Hans is over in Indiana now. A guy named Hans Koch. Some of you may know Hans. And Hans and I did some work a number of years ago when he was at Kansas State. He had a rainfall simulator, and we did several programs around Kansas and Oklahoma, and he did them all over the region. Here's an interesting thing about soil sealing for those of you who really enjoy cultivating your fields. All right, is that we would go out to a site, and he would typically do 4 treatments. One of them was a bare soil that had been recently cultivated. One of them was bare that hadn't been cultivated, and then he would usually have a couple others that were that had some level of residue. I think usually about 30 and 70% residue on those sites. All right. And one of the things that Hans discovered as he was doing this in a much larger region than I did was that it didn't matter what the soil texture was. Regardless of soil texture, After that rainfall simulator put on about 1/4 of an inch of rainfall, the soil profile, the soil surface looked like this. So when we think about how much is actually entering the soil, a big part of it is dependent on how we manage that profile, right? What are we doing with that profile and how are we taking care of it? And so destroying those water stable aggregates, it's very easy to end up with a soil like this. The other thing about that was that same soil that had been cultivated and then had that residue on top of it, he could put on as much as 3 inches before we could get a runoff sample off that same site. So what was the difference? Well, the huge difference was using that residue or that cover crop, whatever you happen to have in place, to capture that energy that's coming in through those raindrops, right? And that's a big thing and of our management, because when we look at that R factor and that USLE equation, what do I have the most control over? All right, I've got the most control over my residue and my crop management, right? That's why it's so invaluable of having good management practices. Now, I know there's a lot of folks who, we spend a lot of money out here to grow that crop. We've got a lot of input costs. We've spent, you guys are experts at taking sunlight and turning it into some kind of biological product that you can sell. Then what we do is we get in our cab and we start driving around in circles trying to burn that off as quickly as possible, right? Is that right? We cultivate, and I understand there's a number of issues relative to that, and I'm not downplaying those at all, because it's a part of the water management. If I'm using that residue to store more water in the profile, now I've got more water it's going to take longer for that profile to warm up. So I realize that we're talking about a real challenge here on management. It is going to take better management decisions to manage it moving forward, because we're going to have extremes of both drought and excess water, right? And then I've got to find that sweet spot for this year's crop, right? For this year's production practices. So when we take a look at what you've done a great job of capturing all of that biomass, or producing all that biomass. But then we get in our tractor and we go around and we burn it off, because really the end product of that tillage is respiration, which is actually, I see Dr. Brzezinski's gone, so I'm not advocating this. I'm just saying this might be a personal preference. If I'm going to burn off my residue, rather than spend all that diesel fuel and going around in a circle, just get a match. Match is a lot cheaper, and it's more fun to watch, okay? I'm not advocating burning your residue, so I want that for the record. This is on tape, right? I am not advocating burning your residue, but ultimately, when you look at it from a chemistry perspective, there is no difference between burning it off with a match and driving around in a circle and plowing it under. Ultimately, it ends up at the same place. Ultimately, what we've done is we're harming and we're destroying those aggregates that we need for our water storage, our water drainage. If you want the water off the field because it's a wet year, improve that structure and get more water moving through that field.
Aren't you enhancing the soil biology, though, if you're incorporating that residue at a shallow depth?
You stimulate, all right? So if you incorporate it into a shallow depth, excuse me, what you've done is you've taken those recently produced material and you basically have given the microbes some sugar, right? So they have this sugar high, and so they will break down what you just put down very quickly, all right? But what you've also done is stimulated some of that long-term, so you brought some material up that had been stabilized, if you will, because the microorganisms at that part of the profile didn't have access to oxygen, as much oxygen. And so now you've brought that up to the top. So not only is there a stimulant from the sugar, but now those more resistant compounds and microorganisms have access to more oxygen so they can burn it off faster. Ultimately, that's what happens in long term. So if we take a look at water demand, again, it goes back to what is your conditions? If we see the variability moving forward like we're beginning to see, we're going to have to manage for both more drought years and possibly more years where we've got maximum water, a record amount of water as we have this year. And so, excuse me. So that's going to dictate really which year you're in of what you're going to have to do with your sites. And it's going to be even more critical to be able to manage those effectively. So if we take a look at adapting, I think the biggest things moving forward, all right, as we take a look at our environment, we've got more variability. Especially in wet years like this, we're bringing more energy into that environment, into that climate, right? And as we are into our region, and as we bring in that more region, we're going to really have to step back and reevaluate some of our management practices relative to soil erosion, because we may be seeing erosion in sites that we hadn't historically seen. And so some of those folks, just getting folks to run their management practices perpendicular to the slope. On a lot of our shallow slopes or less steep slopes, that can reduce erosion 50% just right there. So using wise decisions of how we store that water. If we're in a drought year, what have you done to increase your capacity? A big part of that is how you manage your residue by enhancing that storage capacity. In those wet years, having better porosity, if you will, having more macropores is going to allow you to get that water drained faster, all right? And then when we take a look at our cover crop and residue management, that's the #1 effective tool that we have for both decreasing our erosion that we have, but also our water management, whether that's water storage and or water drainage. So that's one, and so I think there's a lot of work going on right now with cover crops, actually around the globe, but certainly in the U.S. And and I'm a proponent. So if somebody asks me, are cover crops a good thing? Is residue management, is keeping your residue a good thing? I'm going to tell them yes, but that's a different question than should I use cover crops, because that's then going to be a specific locale. That's going to be your production with your equipment and your management practices. And so what I do may be different than what you need to do, because we may have different demands on our system. Overall, though, when we strive for those, we're going to improve, or we're going to be able to better manage and adapt to these changes that we're facing if we can do those two things. All right. And I think, Aaron, I think we're right at the end.